In this lecture presented by www.free-academy.com, we're going to take some practice problem, or a practice problem more or less, on how to estimate the area underneath the graphs. Now this is going to lead into our integral introduction, but our general premise for doing this is fairly straightforward. If we have the graph f of x equals x plus 1, and we want to find the area between x equals 0 and x equals 2, we need a method of going about it. And there's one way of doing it is creating a number of rectangles and such that the upper left hand corner of each one of these rectangles exactly touches our graph here. And because we know what the area of a rectangle is, it's the width times the height. If you add up the area of all these rectangles, you get approximately the area underneath the graph. And there's a general formula for doing this. It's written a lot of different ways in a lot of different textbooks, but generally it looks like area is the summation from I equals 0 to n of delta x f of xi. So what exactly is this saying, especially in terms of this problem here? Let's start out with figuring out what delta x is. Now presumably when we do these rectangles, the width of every single one of these is going to be equal to each other. So the width of 1 is equal to the width of 2, width of 3, etc. So there's a lot of different ways we can do this, deciding on how many rectangles there are. I think I covered before that if you have, say double the number of rectangles, you get a better fit to what your actual function is. But in this case, our number is equal to 4. Now the total area here, the total width of our rectangles all added together goes from 0 to 2. So the width total is equal to 2. Therefore, the width of each one of these rectangles is this total width divided by the number of rectangles, which is 4. So the width of each individual rectangle is going to equal 1/2, and this is going to be our delta x. In our function here, delta x, this is the same as the width times the height up here. So let's plug what we know into our formula so far. We have area is equal to the summation of 1/2, using this as our delta x, times f of xi. But before we go and figure out f of xi, let's figure out what these zeros and, what are our bounds under summation here. We'll take it from I equals 0, because that's kind of a gimme, and we're going to do a total of 4 rectangles. 1, 2, 3, 4. But if we're naming these starting with 0, this is actually 0, 1, 2, 3. So we're going to be summing from 0 to 3. So now the only thing left to figure out is f of xi. F of xi is going to be a little bit different for every single one of these. Or I should say f of x is going to be a little bit different than every single one of these. For example, when we do f of x0, because this is the height of the first rectangle, it should be equal, f of x naught should be equal to f of 0. And this is just something you figure out by inspection here. Our very first rectangle, we already know the width of it is delta x, and the height is the upper left hand corner, where the upper left hand corner touches the function. So this has to be at x equals 0, f of 0 is our height. Now for f of 1, f of x1, you should take a moment and pause this video and try to guess what we're going to put into this parenthesis here, because it's actually something you can figure out fairly straightforward. If our first rectangle started at 0, and the width of each one of these rectangles is delta x, and you're moving over the width of one rectangle, this is equal to our delta x, or f of 1/2 in this particular case. Now we go on and we find f of x2. This is going to be moving over two rectangles. So this is f of 2 times delta x, which is 2 times a half, or f of 1. And then to go on to find f of x3 is going to be equal to 3 times delta x, or f of 3 halves. And the thing to point out here is that if you had more rectangles, your delta x would be shorter. So you would have more of these summation. Let's say if we were doing 8 rectangles, our delta x in this situation would be 2 divided by 8, which would be 1/4. In which case f of x naught would still be f of 0, but f of x1 would be f of 1/4. F of x2 would be f of 1/2. And whatever the width of your rectangle is how many you move over. So now that we have all of this, we can actually plug into our formula here. Our area is going to be equal to 1/2 times f of 0 plus 1/2 times f of 1/2 plus 1/2. This will be times f of 1 plus 1/2 times f of 3 halves. F of 3 halves. Alright, sloppy handwriting there, but you get the point. Or we can have the 1/2 factored out to the front here. F of 0, because our function is f of x minus 1, this will be 0 plus 1, this will be 1. Plus f of 1/2, so 1/2 plus 1 is 3 halves. F of 1 is 1 plus 1, that's going to be equal to 2. And f of 3 halves is 3 halves plus 1, or that's going to be equal to 5 halves. If you add this together, this is 3 halves, 1.5 times 2.5, these add together is going to be 4. 3 plus 4 equals 7. So our total area that we're estimating here is going to be equal to 7 halves. Your formulas may look different depending on your books, but the principle is fundamentally the same. You're going to take a certain number of rectangles, you take your total width of your interval, divide it by the number of rectangles, and then you match whatever corner to your function. You know, it's not uncommon to do, I think it's called a Heaviside approximation, to match the upper right hand corner of each one of your rectangles to your function. Another thing, this is called the trapezoidal approximation, where you take your rectangles, you match your left hand corner, and then you draw a straight line to your right hand corner, which would get you an absolutely perfect approximation in something like this. However, where trapezoidal is really nice is, say your function looks something like this. Your first rectangle goes to here. Say your second one goes to here. You draw the straight line across. And if you take a look, you know, that's pretty minor area. This trapezoidal function, our approximation, forms a really good fit. And this would be opposed to if you're doing a rectangular approximation, where you would get, you know, fairly poor fits. So the best advice I can give you on any one of these problems is, if what your book is telling you is confusing you, throw it away and go with what you know logically works. Because if you put your mind to it, you should be able to derive an equation for any one of these approximations, whether the rectangles are hidden on the upper left hand corner, the upper right hand, or you're doing a trapezoidal or whatever. You should be able to intuitively figure out these formulas if you put your mind to it.